very exciting to have Mark Saroufim with us today. So Mark is a dear friend and colleague, and we followed very similar paths, starting from undergrad at AUB. And we were 1 year apart. I was following him. We both didn't know that I was following him. So first we did an internship at UC Berkeley, 1 year apart, with the same person, our friend Fabien Schreim. And then we did masters at UC San Diego, which is where we met. And I can safely say that my career is divided into two: before Mark and after Mark. So actually, when I met Mark, I was doing my master's in mechanical engineering, and I had never heard of machine learning. And Mark was doing his master's on machine learning theory. So learned a lot about machine learning from Mark. And after Mark, my work has become increasingly more about machine learning, and now that's almost all I do. Mark will be sharing a personal journey, which is from AUB to optimizing PyTorch. For those of you who don't know what PyTorch is, it's the most popular deep learning package, still the most popular?
One of the there's higher level ones these days.
Okay. So
the most popular
to me,
low level one.
All right. So the most popular or one of the most popular deep learning algorithms that's used worldwide. So he'll be touching on machine learning theory, low-level systems engineering, and GPU performance, all the way to his open source work with GPU mode. So I'm sure you'll learn a lot from it. I'm very excited about the talk. So Mark, please take it away. Thanks.
Cool. Thank you, Joe. Okay. Hey, everyone. So for context, I have about maybe 30 minutes worth of slides ready. I'm happy to stick around for questions as long as you'd like to, whether it's about ML systems, ML theory, what it's like working at Meta, my general thoughts about AI, what I think AUB can do better. I'm very fond of hot takes, so please come ask me questions later. And also feel free to interrupt me if you like as well. I wanted to give a background on my field. My field is called machine learning systems, and it's effectively the field of how do you make machine learning models faster. For example, if you've used ChatGPT-4 around 2 years ago, you might have noticed that it was insanely slow. The tokens would sort of generate extremely slowly. And now it's very fast. And making it fast is a whole field, and I'd like to introduce you to this field and how I discovered it, basically starting from AUB, the jobs I had along the way, what I learned, and then why I decided to stick around working on PyTorch at Meta for about 4 years now, and probably for the foreseeable future. All right. So I graduated from AUB in about 2012. So I studied ECE at the time. Joe tells me there's now a computer science program in electrical engineering as well, which is probably what I would have studied, because I was not very good at the electrical stuff. Basically, I found calculus very challenging, and I always preferred discrete math and coding. So my first introduction to AI at the time was this class by Professor Awad, which was called pattern recognition. And what was interesting about this time is it really wasn't all about deep learning. It wasn't really even about statistics for that matter. The primary programming language I used at the time was MATLAB. The two books that were considered the Bible were Pattern Recognition by Chris Bishop, and then AI by Stewart. And for example, let's say one of the problems I did for a class project was this one, which is it's a popular children's book called Where's Waldo? And the goal is to find Waldo. Waldo is this gentleman here with the red stripes, and you have to find them. Today, if I asked you to solve this problem, what I would suspect most of you might do today is just input this image to an LM and ask where's Waldo, and put a circle, and it would probably find it. At the time, the solutions were a lot less obvious. For example, the way I ended up solving this for my project was doing a fast Fourier transform on this image, and then and then red and white stripes have a very particular pattern, and then you train a simple classifier to find that pattern. So again, it was a very, very different field 10 years ago, 12 years ago. All right. And I also remember very fondly, I don't know if this is still true, I hope it's not, but when I was graduating from AUB, the primary job everyone wanted was management consulting. I remember in a class, they asked us what people want to do, and about 90% of my colleagues in ECE said they wanted to go into management consulting. You basically get the Rolex, you get a BMW, you go live in Dubai. And for me, this was never particularly that appealing. I understand the appeal, but I got really lucky, and it's kind of how I ended up meeting Joe. Was I got an internship at Berkeley, where the goal was we had these basically these little robots that we would throw in a lake, and they would calculate the flow in the lake. And I was like programming them, and then they would sometimes get lost in the lake, so I would need to go kayaking after them. And it was like probably one of the strangest internships I've had to this day. But like what I remember like feeling very fondly was like it felt like an environment where people cared about like engineering, like they were curious about building stuff. And I hope that like AUB's culture is like sort of slowly moving more towards this versus this. Yeah, I mean, again, it's how I ended up meeting Joe, and I do really want to plug. There was like I don't know if she's still at the UB, but there was like Nadia Mfarij from the Career Fair who helped me find this opportunity, and it was like very life changing. So if she's still here, I just want to say thank you. All right. So again, at the time, the field was sort of like wide open, right? It wasn't necessarily clear like these are sort of the most interesting problems, and so I just picked what I was curious about. I went to UCSD. And UCSD at the time, and it's in San Diego, it's very sunny, very nice, you get to wear flip-flops. It was mostly known for its neuroscience program. So it was like really a top tier like bioinformatics and neuroscience program. And like my thinking around the time was, okay, well, if we can probably like mechanically build something that looks like the brain, we'll probably end up with AGI. So this was sort of the reasoning, and the sort of like core theory behind this was something called spiking neural networks, which is contrary to the way neural networks work today, as in like you have a single linear, which is like a matrix multiplication, you would actually model the dynamics of the neuron in this case. Thankfully, and I abandoned this idea in about 3 months because it really wasn't clear at all to me why this would lead to AGI. It seemed interesting, but not necessarily where I should be spending my time. And UCSD ended up being like a very, very nice environment to study more like harder things that aren't necessarily possible in industry. Like for example, like I wrote a small ebook on discrete math. I taught a quantum computing seminar. Like I gave another seminar on game theoretic probability theory, and my thesis was on computational geometry. So at the time, I was like very, very passionate about math and ML theory, and this seemed like to be like a nice place to do it. And again, it wasn't necessarily clear at the time what are sort of the important ideas, right? So I was just absorbing where I thought like interesting ideas existed. All right. So my first job, this was right straight out of UCSD. I went to live in Seattle, which is very, rains all the time. I don't recommend living in Seattle. But like I tried all the disciplines there. I was a product manager, I was a software engineer, and I was a research scientist. And it was very unfortunate because like AI was still too early at the time. Like for me, I was like very convinced from very early days, like this is probably the most important thing to work on. But to give you some context, like basically one of my first projects was an email importance classifier. So basically, instead of like just getting all your junk email, because more than half email that you get is typically machine generated, not human generated, that we would have a simple classifier and it would decide, is this important or not? And then you just have like an inbox of important things. I had a model that like worked pretty well, and it was a 50 megabyte model. And ultimately, this was considered too large to ship in production. And today, just for context, like we're basically at a minimum of 26 gigabytes for any sort of like interesting LLM. So like basically the industry really, really changed in the last like 10 years. The other thing is that like the thesis at the time among like senior leadership at Microsoft was that the internet data is mostly low quality, useless data. And so you shouldn't spend time training models on public data. You should spend time building data pipelines internally to generate like high quality enterprise data that might be useful in a few years. So the idea was like ML might be useful, but just like not today. And I also felt this was wrong. And this thing that convinced me, there's something a lot of AI people go through called their field AGI moment. Like field AGI moment is like the moment that you felt when like AI could potentially be smarter than humans. So for me, I'm a lifelong strategy gamer. I used to play a lot of chess like growing up, and then like I played a lot of Dota. And for me, the field AGI moment was getting destroyed by OpenAI's like Dota 2 bots. And I was like, huh, interesting. Like the behaviors they exhibited were interesting. Like these models were deceptive. They would trick me. They would outsmart me. They would trash talk me. And I'm like, huh, like this kind of technology is possible. To me, seemed like sci-fi at the time. So I quit my job, and my mom got really upset at me. And I wanted to build a company for AI for game developers. Unfortunately, this turned out to be like a very bad strategic bet for a few reasons. Like the primary one is that like I didn't have a lot of money, so I couldn't like really use a lot of GPUs. Reinforcement learning as a technique is very sample inefficient. And so it cost me not necessarily 20K in dollars, but more like in terms of my time, like a month of training time to get something. And it would be extremely unreliable and brittle to the starting location. And even then, like, you know, it was just me. So like, why would a company like give me these large amounts to go train a model? Like just like something was off. So I decided to go get a job. And the job I got was at this hardware vendor called GraphCore. And the way it works, and I'll talk a lot about GPUs like throughout most of the talk, But we basically have like CPUs, which are, like you have GPUs, which are a SIMT architecture. Like you basically do many dumb things in parallel. And the core idea of an IPU was that it was like a MIMD architecture, so different cores could communicate to each other. The TLDR is like they took different computer architecture trade-offs. The core one being you have a very small amount of very fast SRAM, as in the total VRAM on the chip is about 300 megs. To compare this to like an H100 by NVIDIA, that's about 80 gigs, just to give you a sense of the order of magnitude. But as long as you can fit your model on this like very small cache, it's gonna run like 5 to 10 times faster than it would on a GPU. The problem with this thesis was that like essentially the hardware architecture was betting that models would get distilled and become smaller, when really the opposite happened. Like models got like significantly bigger as we move towards LLMs. And so now like if you have a 26 gig model, how is it gonna fit on 300 megs? So now we're building a compiler that can like basically automatically partition your single model over like a whole grid of chips. Compilers are unreliable. Might not be able to predict all sorts of like settings or models that users might have. And as a result, the customer experience was really bad. And so we really suffered to get adoption for the hardware. Very tangentially, not that tangentially, COVID started and I was spending a lot of time at home. And I remember I was spending easily in the first few weeks of COVID, like 5 to 6 hours on YouTube a day. And so I was like, okay, my wife told me like, you're spending too much time on this. Like, why don't you just like make your own videos? And I'm like, okay, sure. I'll make my own videos. I'll write my own blogs. And what was interesting, and I started doing this like basically partway into GraphCore, and it was really interesting because I got introduced to open source developers, like people that were building things in public. And this kind of like gave me permission to start working on interesting projects, even if like at the company things weren't going like very well at the time. So this is how I discovered PyTorch. Essentially, I discovered PyTorch by accident. So what is PyTorch? Like PyTorch is a programming language to author like machine learning models. You write in PyTorch, and ultimately this dispatches to like fast CUDA kernels that will run fast on your GPU. And the key thing that's like really hard to like overstate is that like at the time, like a lot of machine learning frameworks existed. We had TensorFlow 1. You could do machine learning in MATLAB. There was an open source alternative called Octave. There was like Theano. And all of these frameworks had the sort of problem that like they were hard to program and your code didn't look like your math. So the aha moment for me was basically this. So this is a UNet model. So UNet is an image segmentation model. And I remember just opening the paper, and then within like an hour or two, I already had like the model implemented on the right. And so for me, this was like mind-blowing. Like essentially, the way the UNet architecture works is like these are all like convolutions that have like different inputs and output sizes. So this is what these down projections are. And then you have up projections where you increase like the size of like your output layer. And so I could just like write it like in this way, like with like self down, self up. You could print things. This was considered revolutionary because in TensorFlow 1 you could not. So it was like easy to debug and reason through. And again, it just didn't take me like all that long at all. So I decided to like apply to work on PyTorch. Okay, so if you go to the PyTorch GitHub today, basically the most succinct way of describing what the project is it's a GPU accelerated tensor computation library with autograd support. So a very simple example is here, like you import PyTorch, you instantiate two like random matrices, you multiply them, you take their sum, and then you do a backwards pass. This was revolutionary for a number of reasons. Like back in my day, I would derive backwards passes by hand. Like you would basically need to know calculus, and you would essentially like just write everything. You would write out all of your backwards formulas like by hand. This was extremely error prone, and bugs in autograd were extremely common, even for toy models, let alone large ones. And the benefit of frameworks like PyTorch is that you basically only write your forward pass code, which is like very easy to author, and you get the backwards pass for free. The other thing to keep in mind is like it has GPU acceleration, and why is GPU acceleration important? The basic example, like if you're not really familiar with GPUs, like you can think of them as very shallowly as fast matrix multiplication machines. And if you'd like to learn more, I'd highly recommend you like attend Professor Hajj's class on like CUDA, which I think is in the computer science department, right? Yes, okay. I highly recommend the class. And basically, like in that class, you'll learn concepts like, well, how do you write like a fast matrix multiplication algorithm on GPUs? And this algorithm and this like innovation by like NVIDIA is really primarily responsible for why the company became like close to a $3 trillion company. There's a big dip there because of tariffs, but outside like of that, Imagine this goes to infinity. So matrix multiplication is the most optimized algorithm in human history. It's like 200 years old. It's also probably the most important algorithm in human history. And so learning how to make it fast on GPUs, really, really worth your time. And the reason it's really worth your time as well is because like model architectures have converged. Like when I was in grad school, there was like a whole bunch of algorithms that were important. And so getting them to be fast was often like a bet. Like you would need to bet on what would potentially be important in the future to then write very hyper-specific code for it. Whereas today we know what algorithms are important. It's basically attention-based autoregressive language models. And for anything that's larger, it's mixtures of expert models that are on the right, which are becoming like a lot more fashionable with models like Llama 4 and DeepSeek and et cetera. And so because like the architectures have converged, because like they were, the architectures have converged primarily because of scaling laws. So scaling laws is basically, this is like an older paper by Jared Kaplan, who was at the time at OpenAI, now at Anthropic. And what they did is they basically made like a physics-based argument where they're like, okay, let's try varying the amount of compute, the amount of data, and the number of parameters in a model. How does this affect the final training loss of the model? And they basically discovered that there's effectively like a linear in-log scale relationship between like all of these parameters to like the quality of your model. And so if you're very ambitious, you look at this, you're like, like what would happen if I like made the compute side of this equation $500 billion. And this is exactly, for example, what the current US administration is doing by funding like Project Stargate, which is a $500 billion cluster over the next 4 years for OpenAI to build a data center in the US. So scaling laws have a few interesting properties, like basically saving costs is obviously important here because if you save like a percent, let's say you save 10%, like that's $50 billion, you save a percent, that's $5 billion. Like these are large values and efficiencies are always appreciated in a field like this. Again, this is very different from what an ML curriculum looked like. I don't know what your ML curriculum looks like today, but mine looks something like this. It was things like topping modeling with latent distribution allocations. We had like graphical Bayesian networks, like support vector machines, like A-star search. These are all sort of like important ideas and they come back in like various shapes and forms always. It's not like they're obsolete necessarily. But again, if you're like a performance person, you don't want things to vary. You want the workloads to be very fixed because every time a new hardware architecture comes out, you want to like optimize like the heck out of it. And not knowing what researchers want just will make you anxious. So knowing it helps you make things like very, very fast. All right. So I talked like basically at a very high level, like matrix multiplication. Like why is it such an important algorithm in deep neural networks? So this is an example from like the attention is all you need paper. Like this hasn't changed like all that much in like existing models, like with the exception of MOEs. But matrix multiplication shows up in like 4 different places here. It shows up in the embeddings. It shows up in the feed-forward layers. It shows up in the linears, and it shows up in the attention computation, which is QKV. And so fundamentally, the way you can think of it is when you say a deep neural network, you have layers. Every layer is a weight matrix. So this is like this weight in, weight out. The activations or the input are this input. And so every layer is effectively computing a matrix multiplication. And this is kind of why matrix multiplication is a very, very important algorithm to accelerate. All right. There's also other interesting properties to this, and I kind of want to make the point that like some basic law knowledge of linear algebra really helps here. Let's say that like an individual matrix, like the weight matrix, is larger than 40 gigabytes. So it's not going to fit on a single GPU, and you need to shard it over multiple GPUs. Well, it turns out there's this nice like linear algebra property in that you can split the matrix like column-wise. You can do the computation over like chunks of this input. So instead of like 40 gigs, it's 40 divided by 3. And then you can concatenate the result. And so this is sort of like the core idea behind a lot of like distributed training. They also have to worry about communication bottlenecks, but like at a high level, this is like how much matmols show up, like and why they're so important. All right. So this is what a GPU looks like. So this is a consumer card, like a 3090. This bus, like this thing here at the top is called the PCIe switch. And if you have a gaming PC, like you will just like physically plug this in. And then your GPU is often like bottlenecked by how quickly the CPU to the GPU can transfer data through this thing. This is what a more modern GPU looks like. This is an H100 data center GPU. The way you can think about this is, where is it here? So this part here is the actual compute, like basically where the matmul is happening. This is called high bandwidth memory. So basically, how do you, where do you store your weights such that you can do computations on them? And then most of this is just power. And I think this here is communication, if I'm not mistaken. But like the majority of the chip goes towards like supplying power, because even a card like a 4090 takes close to like a kilowatt of power. And just for context, like in a typical home in the US, you can't draw more than a kilowatt of power like from your wall. Like you'll just physically blow up your fuses. So it's a lot of powers, and I have one of these guys, and I can see how it affects my electricity bill, and it uses about as much electricity as my washing machine. All right. So again, the core idea here is like, and I mentioned in the beginning that like models like GPT-4 used to be very slow, but now they're really fast. Typically, this is measured using tokens per second, like how many like physical tokens can you generate, and that's why it sort of generates them one by one. It's an autoregressive mechanism as well, where you look at the past tokens and generate the next one. And I just want to give you like a sense of the orders of magnitude of how long these take. So for example, like GPT-4 like takes like about like 40 tokens per second, which is like extremely slow. But then like, where is it? Like O1 preview, wait, where was it? Yeah, like, this is the slowest one. So there's two metrics here, right? Like latency here is like the time it takes to get the first token. And then you basically get the tokens per second. So like if any caching you need to do, that happens at the beginning in latency. So again, like you can sort of like back of the envelope this a bit. Like how many tokens are in a book? How many tokens are in a paper? And like if you can run, like I don't know if any of you have used deep research. It's very slow. It takes about like 15 minutes to generate stuff. If it can take like a minute, then using it becomes qualitatively different. You can basically use it interactively. But right now we're more in the batch regime because of how slow these technologies are. And they don't need to be. It's just that like we need more people to make it faster. All right. So I talked about PyTorch a bunch. I just want to give you like an idea of what it's like to program PyTorch. And then I'm going to talk about GPUs for a second and how they relate. So in PyTorch here, the first line is here. The second line is we're creating a tensor on the GPU. This means we're allocating a bunch of GPU memory on the high bandwidth memory, so the thing I showed you here. And then we, let's say, want to add 1 to this tensor. Adding 1 to a vector is kind of ill-defined, and so what we do is we broadcast it, like this becomes a vector of 1, 1, 1. We add it all up, and then we print it. Printing is interesting, and this is why like other frameworks did not support printing in the beginning, is because GPUs are asynchronous. Like you basically like dispatch a job to the GPU, and then you wait until the result like finishes. A print forces a synchronization. Like you're basically telling the GPU, no, I want to know like what's in this location of memory. And then like, let's say we want to like do other operations like a cosine. So we basically read X from memory. We do a cosine operation. We write the results back to memory. And then we read the results again from memory for X. And then we run a ReLU operation and we write back the results to GPU. So there's like this like big back and forth. But historically, this trade-off was fine, and it wasn't too slow to do this kind of programming model because GPUs weren't particularly fast at the time. Like GPUs were slow enough that like this async overhead wasn't like a huge deal for like 5 years of PyTorch's life. This is very small font. Okay, I want you to pay attention to 2 metrics here. So this is what's called a data sheet for like an NVIDIA GPU. And for an H100, which is like the last generation like GPU, and B100s, you can't really buy them today, so this is just the H100s. So first off here, where is it? The clicker here. All right. So you'll notice here that, like, for example, if we're doing like FP64 operations, we can do about 34 teraflops. But if we're doing something like FP32, it doubles to 64. But like if we go to FP16, it goes to 2000. So this jump was interesting, and it's when compute basically stopped being the bottleneck. And instead, the bottleneck became this, like memory bandwidth. So memory bandwidth is how quickly you can send data to your GPU. This has not increased all that quickly on every GPU generation. But the actual compute has dramatically, as especially we go to lower bits. So this is on H100s, but on newer GPUs like B100s, we have like the MXD types like FP4, FP6, and FP8, which can increase like the total flops even more. All right. So the reason why memory bandwidth is a big deal is a pure physical problem, as in you have your CPU and it needs to physically send data to your GPU. So there's just a wire between them. So in theory, you're bottlenecked by the speed of light, which at these numbers becomes like an actual problem. And then the second problem is in practice, you're not really bottlenecked by the speed of light, you're bottlenecked by the speed of electrons, the speed of electrons in copper. And this is not like something that's easy to solve. It's like a hard physical problem. So let's say like I have a hardware startup idea, which is I just put them really close to each other. Like the CPU and the GPU are almost touching, such that these wires are very small, and it'll go much faster. Well, there's another physical problem here, which is Dennard scaling, which is that like it's going to be too hot. And this isn't solved. Like you can put them physically close to each other, like horizontally, it'll be too hot. You can stack them on top of each other in 3D, it'll still be too hot. So this is a problem that does not have like a clear solution with the current like programming model of GPUs. So really, and kind of why I like, because sometimes people ask me like, what is the benefit of like sort of a generic CS education? I really want to make the point that today the progress in machine learning is being bottlenecked by progress in GPU compute, which is bottlenecked by progress in computer architecture, which is bottlenecked by progress in manufacturing, which is bottlenecked by progress in physics. So if you work on any of these, you can have like an impact in ML systems. So please don't drop everything you do to work on AI, like become an expert in a subfield and then come help people in AI make things faster. All right. Okay, so I want to give you like another way of understanding this memory bandwidth problem here, which is like arithmetic intensity. So let's say we want to do what's called like a ReLU operation. So a ReLU operation is you go over every individual element of a vector, and then you check the max of it with 0, and then you just like write that value back. So it's like this shows up a lot in like deep neural networks. It's an example of what we call a pointwise operation because it operates over every point of a vector. So let's assume every element in this vector is a float 32. We first need to read every element of this vector because it's FP32, this is going to be 4 bytes. We're going to do one comparison operation with 0, and then we're going to write a value back. So the arithmetic intensity is basically taking the number of ops, like 1, divided by the total number of like memory reads and writes, which is 8. And if this value is less than 1, you are memory bandwidth bound. And for a lot of things we want to do in deep learning, like we are unfortunately like memory bandwidth bound. Most notably, autoregressive decoding in LLMs at batch size 1 is memory bandwidth bound. So this is why like we care like a lot about this problem. So okay, I'm gonna do a pop quiz. What happens if instead of this data being in float 32, it's now in float 16? Does the model become faster or slower, and like why? Joe, humor me then. No? Okay. All right. So it's gonna become faster because like we're reducing the arithmetic intensity. So instead of like because we're bottlenecked by the speed at which we can send data from the CPU to GPU, if we're sending less physical data, it's gonna be faster. So that's why quantization is really important and why I spent most of last year working on quantization in PyTorch. I also wanted to give you some sense of what I call VRAM math. So for example, like I'm sure like a lot of you guys might have used like a model like Llama 8B. So how much VRAM will this model take? Like turns out you can actually compute this like very rigorously, which is that like Llama 8B is a model shipped in FP16. So it's about 2 bytes per parameter. So Llama 8B takes like 16 gigs. So this is inference only. If you're also doing training, you need to add your gradients, which is basically the same size as your parameters, like another 16 gigs. Your optimizer is frequently an optimizer called Atom, which has 2 parameters per weight value. So it's about 32 gigs. And then there's also your activations, which is basically the intermediate values. This one is a bit harder to compute easily. It's model dependent. But the core idea is that like this is the main bottleneck for very large batch sizes and large sequence lengths. And it's why like supporting infinite context windows can be really expensive and why a lot of like LLM services don't provide it for free. And just to give you a sense of like budgets, like a 4090, which is like a very expensive consumer card, is about 24 gigs. An A100 is 40 gigs, and then an H100 is like 80 gigs. So these are like roughly numbers that I've like memorized, and I always do this kind of like back of the envelope to know if things will fit or not. So here, like I mentioned, we have this problem here where we need to read X, write the value back, read X, and then write the value back. So because we're memory bandwidth bound, we need a good solution for this because here we're physically sending X over the wire back and forth, and this is very slow, and it is like the main bottleneck. So instead of what we do is we're like, okay, well, instead of writing the value and reading it twice, we do it just once. So for example, let's say we want to do a torch square, which is like we go over every element of a vector and then we square it. instead of like squaring and writing the value back, we just square twice and write the value back once. So this is an example of what's called a fusion. And a fusion is probably the single most important optimization you can do in any sort of machine learning model. And this is how Torch Compile works. Like Torch Compile, its job is to generate these fusions for you for free. And again, yeah, fusion is very important, memory bandwidth bound, autoregressive modeling, blah, blah, blah. Okay. So with compilers then, like a very natural question is that like, why do you need to write GPU code again? Like why can't like compilers just write all of it? And so I really like this exchange from the Flash Attention 2 Open Review. What Flash Attention 2 is the single most popular CUDA kernel like in existence today. And it's a kernel that specifically optimizes like the attention head part in like attention models. And so like one of the reviewers asked, do you think a compiler could realistically generate Flash Attention 2? And the key part is that like probably not, because like compilers are very good at doing like dumb optimizations like fusions. But for things that require like mathematical rewrites, such that you preserve the numerics of your model, but it happens to be faster on the hardware, humans are better at it. And maybe someday LLMs, not today. Like today, we basically have very intelligent humans spend about 2 years porting Flash Attention from A100 to H100. And this is probably going to continue to be the case. So we're very like talent bound as well in these problems, not just memory bound. So concretely, like, when you think of PyTorch, we're a very flexible framework. Like we don't know exactly what kind of code people are going to write. And so we basically need to support like all sorts of things without like exploding our code size. So some examples of easy kernels that we might want to support are like fusing a matmul with a nonlinear activation like a ReLU or a GeLU or a Lulu or whatever. So these things, we want to support them via compilers, but then for hard kernels like matrix multiplication or Flash Attention, go watch Azat's class and you'll see like how to build those things. All right, so this is a very opinionated take, so I am warning you a bit, but there's like a big spectrum of how to program GPUs. On the sort of extreme spectrum, like over there, you basically have math. Math is interesting because it's forward compatible, as in like matrix multiplication is probably going to continue existing as an algorithm for as long as we're a civilization, but it also doesn't have any implementation details. Slightly lower level, we have frameworks like PyTorch, like their goal is to maximize like researcher productivity, but like performance isn't the main goal. There's since been alternative GPU programming languages like Triton that are like what we call like a tile-based programming models that are significantly easier to write than CUDA. And then there's similar ones like Thunder Kittens and Cutlass, which are like really good for like writing like very fast matrix multiplications. And then sort of at the lower end, we have things like CUDA and PTX, which are very good for like surgical improvements in your model, but might not necessarily be the best fit as you're like authoring your model and trying to explore which ideas work and do not. Okay, this is a busy slide, but like the main thing I wanted to show you here is that like writing Cutlass is generally pretty hard because it's very templated C++. It's hard for humans to write, it's hard for machines to write. But like what we can do is we can get compilers generate C++ code. So we can read the Python code and generate fast Cutlass code. So this is an example of how we might do this. And typically the way these benchmarks are done is we'll look at a popular model like, let's say like Llama 70B. We'll look at the shapes of the matrix multiplications in those models, and then we'll optimize like those shapes specifically. So for example, here, like at the bottom, you can see like the specific shapes that like we're optimizing for, like the QKV, the first weights, the second weight, etc. And these are like the weight values here, like at the top right here. So again, like matmul is very shape dependent, and the more constraints you have on your problem, the faster you can make it. So yeah, the TLDR, is like the world wants performance. Flexible frameworks like PyTorch can solve fusion problems, but not algorithmic systems problems. And custom kernels are here to stay. So I would suggest y'all learn how to program GPUs like a bit. And the barrier to entry is getting easier, both because of like better programming languages like Cutlass and Triton, but also because of like meta-programming techniques like Torch Compile. Okay, so I just want to end with like a few closing notes, which is like, let's say this talk was remotely interesting. Like, how can you actually get started in ML systems? So I suck at giving advice, so I'm just going to tell you what I did. So I worked on PyTorch for about 3 years, and throughout these 3 years, I felt like my own understanding of how GPUs work was very shallow. And so I decided to just like learn CUDA really thoroughly, and this is the book that I got, and it's very good, and this is like where Azat's name's here. We basically started a community on Discord for people to just read this book on a weekly basis. And it kept growing. Like basically, we have like close to 16,000 like members on our YouTube channel, and we have like weekly lectures if you're interested in like various GPU programming techniques. I use these lectures as a way for me to learn how GPUs work, and we've been doing it for a year, and I don't see myself stopping anytime soon either. But where it got really interesting was instead of it just being a chat group where people watch lectures, it also became a place for open source developers to like organize, self-organize, and build cool projects. So the most famous project we had was LLM.c. So this was like by Andrei Karpathy and a couple of other famous developers who built a full LLM pre-training pipeline in raw CUDA. There's other projects like Liger, which is like Trident kernels for LLMs, Torch.io, which is a Pythonic quantization library where I was one of the co-creators, Trident Puzzlers, which was a short curriculum to learn Trident that's very efficient. And my most recent project and what I'm working on today is an LLM that can generate CUDA and Trident code called Project Popcorn. So if you're like looking for good projects, then please join or create your own working group on the Discord server. Where it kind of got interesting as well is this started happening last year, where like communities have a lot of power. So we had like this like one in-person hackathon called CUDA Mode IRL at the time, and we invited only about like 200 like very technical people to come hack. And what I found interesting as I was raising compute credits for this event is that like with no negotiation, I raised about like $300,000 worth of like cloud credits and another $200,000 like cluster from NVIDIA. Because people like, this is how important this problem is. Like people want you to make their GPUs faster and they're willing to give you an abundance of money. So take it and go make their GPUs faster. So last year we were planning one event. This year we're planning 10. Like most of them are in the US. We're hoping to do one in Europe and Asia soon. So I will let you all know. All right, maybe I can skip this here. Okay, actually maybe I'll cover this for a second. So like, for an example, like I also want to maybe expand the horizon a bit. Like there's a lot you can do in performance outside of just writing CUDA code. Like what I was interested in is sort of like just making people more productive at writing kernels, period. And so we've been working on this project called Project Popcorn, where one, there aren't enough like known eval suite for how to measure how good LLMs are at writing GPU kernels. So we built an eval suite called Kernel Bench. We also built like the largest ever kernel data set in the world, and we want people to study it and use it and plagiarize it and build an LM. We also have a platform for competitive GPU programming, so very much like LeetCode or Kaggle for like people to write fast GPU code. And we used all of this to train an LLM that can write Trident code. And this LLM, like an 8B model, like managed to match like the 670B DeepSeek R1 model. And for us, this is very much like the beginning, and we're like, I'm really looking for good ideas in the space of people like optimizing these models. So let me know if you're interested in this. Okay, so this is sort of the competition platform I talked about. Like basically, if you're sort of looking for which problems are worth making faster, join our competition platform. It's free. You basically get free H100s, A100s. If NVIDIA gives me a B100, I'll take it. We also have free MI300s from AMD with lightning fast cold start. So it's like as if you like own them. And we release new problems on a weekly basis. And so this thing I'm most excited about for today is we just announced this yesterday is we just announced a competition with AMD where you can win $100,000 if you can write the fastest reasoning kernels on MI300. So yeah, I mean, if you're even remotely interested in the space, there's going to be like a lot of attention, a lot of people learning from each other. And like 100K is like not bad. Like it can be life-changing, and hopefully you can use that money to buy even more GPUs. All right, so this is my last slide. We really need more people working on ML systems. Regardless of your expertise in engineering and computer science, like there is a space for you. This talk could have easily been like 3 hours long because I didn't cover distributed programming, sparsity, hardware, software code design, but please ask me questions. Your goal as you're thinking about this is you should think about like, how do you accelerate problems that other people care about? Like that's like the most important metric. Like that is like what will make you famous, like get you to have nice jobs. And if you don't know what other people care about, like communities are a good hack for this. Like you can just see what people are talking about. And that's why I have GPU mode. That's what I use it for. Like I mostly look at for what people want, and then I just go build it. And I've been doing this for like a year and a half now. So yeah, if you're looking for more advice on where to start, please ask me questions. I hang out a lot on X as well, so feel free to message me there. And yeah, thank you so much, Joe, for inviting me.
Hi, Mark. Thank you for coming and giving us this talk. It's great to see you. I had a question. Usually people, they start off in HPC and systems, and then they kind of gravitate towards machine learning because machine learning is hot. So you kind of had the opposite trajectory of starting from AI, machine learning, and then making your way towards systems. So I was wondering, kind of in that direction, from that perspective, what were the challenges that kind of you faced starting off not in systems but in AI and then making it into systems? Was there anything particularly challenging?
Yeah, like it's an interesting question. Like my observation here was that like when I started my career, especially like when I say start, it's like really UCSD where I felt like I was like very deep into AI for in theory. And my main problem was that I couldn't know, like a piece of paper can't tell you when you're wrong. And like this has like important implications. Like you can write a proof, and I could write a very lengthy proof and convince myself that it's like correct, but then if there's like a subtle bug, I wouldn't know. And so like I was always like interested in numerical computing primarily as a way of understanding like ML theory. Um, but like fundamentally, I would say like it's probably a harder route than the other way around, which is why like most of the successful people I know in this space are systems people first. There's a caveat to this, which is like if machine learning models change a lot in the future, then the systems people would have hedged incorrectly. Like basically it would have been important for you to go understand these algorithms. And like now you're like, you don't have like that knowledge. But as long as we're like sort of in a regime where architectures are constrained, saving costs is important, then yeah, like then the systems people made like a better long-term career bet.
I have a question. So many people now are trying like to build LLMs that don't need a lot of memory or a lot of space and a lot of processing. I think you've mentioned a bit about this, but don't you think this might like move the attention on building GPUs? Like if somehow we reached a way, I don't know if this is really possible, but if we reached a way to do the LLMs on CPUs, so we'll be able to do this?
Yeah, so I think there's like there's two parts to your question, I think. Like one is like techniques for making models more efficient are of course very interesting. Like basically, this is broader than just writing kernels. It's quantization, like lower bit, there's like sparsity, and there's distillation are sort of like the three key ones. Um, I think these are all very interesting, like just because you basically as a person need to make like a cost versus efficiency trade-off. And for a lot of like these bigger labs, they just effectively can neglect this equation because they can just like raise more money, right? So you as an individual, it's very challenging for you to do this. And for what it's worth, like even though I work at Meta for context, like the 90% of my work is on one GPU, usually an A100, and the other 10% is on 8. So like I've maybe ran 100 job once because I needed to just to validate. So, so that's one. I think research and efficiency, I think will continue being extremely important and fruitful from a career standpoint. The other aspect is like, well, like if the models get small enough that the matrix multiplications don't need to be so big that they need to be on a GPU and they can fit neatly on RAM and you can still run vectorized instructions on CPU, then yes, of course, right? But the bet is this, like basically the bet is the average matrix size gonna go down over time or is it gonna go up? So far, going up seems more likely to me. But if it does go down, then of course, like CPUs are like in a much better position strategically.
My question is, what did DeepSeek do that was different in terms of utilizing their limited number of GPUs to train their models?
Okay, I mean, there's a lot, right? So let's see. I think I'll see if I can remember all of them, but I'll just list out the ones that can come up to mind. So the first one is they had a very fast floating point 8 matrix multiplication algorithm. So like generally for these things, basically like NVIDIA needs to make the hardware available with floating point 8 support. And then whoever does it really fast has like a big advantage, but they have to do it fast. Like you basically have to drop everything, make it fast, and that's like one of the main things that they did. The other one is like instead of like doing like per token, like instead of doing like autoregressive per token, they predict like multiple tokens at once, and this is like called MLA. It's sort of like, it's an interesting sort of like algorithmic innovation in this sense that also basically is convenient from a systems perspective. And this is what we often call hardware software co-design. Like basically designing software algorithms that would be amenable for the hardware. So that's two. The third one I can think of is So there's like interesting constraints. Like for example, most modern file systems today will cache results because they make an assumption that if you read a file, you're likely to read it again, right? This assumption is not true for machine learning training. If you read a batch, you're probably never going to see it again because we typically do one epoch training. So they designed the file system with no caching. So generally, so that's 3, 4, I forget. And then the last one was, so NVIDIA has a distributed systems library called Nickel. So it's basically the programming model is like MPI. It's like a very HPC sort of thing where you can from one process send data to another process. So MPI wasn't giving enough opportunities to the DeepSeek team to overlap communication and computation. So they basically used like lower level assembly, PTX, to do so. I think there's like 1 or 2 more that I'm missing, but it wasn't like 1 or 2 things. It was like a whole set of like interesting systems ideas. Granted, I've heard like the sort of idea that like them training the model at like only 50 million. I think this is like a bit fake news because like that was just the winning run, not all the runs that led up to it, not the labor cost. It's not even clear if that's like the entire model because there's export laws between GPUs and China. So like there's sort of like a lot of asterisks, but like fundamentally the sort of algorithmic systems innovations that I mentioned were very real and very, very interesting. And I suspect they'll be very standard in other LLMs very soon.
I have a question.
Yalla.
So the scaling laws are usually, bigger is better. The question is, how much is it dependent on the hardware? And since there's a limit, which is the physics, how close you can put the CPU to the GPU. So communication is part of the limit.
That's correct, yes.
Do you think the scaling laws will change as we have hardware innovations? And do you think, is there a limit that's just a physical limit that we cannot actually do?
So the scaling laws don't make an argument based on like GPU count. It's more like on compute count. And so conceptually, if like another piece of hardware can also do training, then it can like basically make the same kind of arguments. Unfortunately, most hardware vendors ship inference-only chips. So training is typically the realm of GPUs only, where there's only 2, 3 real competitors, like basically like AMD, NVIDIA, and Google with TPUs, which is a slightly different architecture. But you are correct to say that like there's sort of two things. Like one is scaling laws like are like logarithmic, right? So it's not like you get diminishing returns. And in the face of diminishing returns, like you can have one of 2 attitudes. Like you can say, okay, maybe that's enough. I need to do something else. And then you're like, no, like why not 100x the compute? So this is like a very different attitude that like OpenAI had, which turned out to be like a correct bet. I think the last part of your question is around like communication bottlenecks. So a lot of these big models are effectively like communication bound at like 1,000 plus GPU is fully communication bound. And so that's why like the world is basically moving towards like what we're calling like asynchronous training. So the core idea behind asynchronous training is that like let's say one GPU is training a model and then another GPU is training the exact same model. Typically in distributed compute, they communicate their weights after every single batch. And they're like, okay, like I got these gradients, you got these gradients, let's average them and let's average them. So the core idea is like, well, why should they communicate every batch? Why not every epoch? Why not every 5,000 times? And historically, the problem with asynchronous training is that like it's not reproducible. As in, for example, basically, let's say you have 1,000 GPUs and one of them goes down. In the old world, you would stop everything, spin up another GPU, and then keep training. And your results will be numerically exact. But now, let's say you have 1,000 GPUs, one of them dropped, you keep going, your global batch size is now smaller, your numerics change, and this used to be a big deal, but now it's not. Now it's not a big deal because it's not like we're running multiple experiments on these data centers. We're running a single model that's consuming 100,000 GPUs. So stopping it means you're losing like millions of dollars per minute. So you don't stop it, you just keep going. So like I think the sort of economics of it has meant that we're going more towards asynchronous training. And I think actually back to your original question as well, asynchronous training is also one way of training models at smaller scale within a community because you can, for example, you as AUB share GPUs with like another lab, and that can be part of the same job because it's asynchronous. And in an asynchronous setting, this is not possible because you'd be bottlenecked by the speed of the internet. So I think it's very interesting, and it's like one area where I think more people should be thinking about and spending their times.
You were saying that because of heating purposes, we cannot, it's not physically possible to place the CPU next to the GPU. So I was wondering, I know when using CUDA, we usually allocate memory using on the CPU, and then we transfer it to the GPU. Do you think we can reach a state where we only depend on coding on the GPUs, and not going through the CPU as an interface, relying on GPUs only?
Yeah, so this is a different trade-off in the space. So basically, MacBooks, masalan, they have what's called unified memory, which is your CPU and your GPU share the same like amount of memory. This means that like there is no transfer because it's the same memory. The trade-off with this architecture is that the performance becomes unpredictable. For example, you're training a model and then you open Chrome. And now Chrome is using like 8 gigabytes like of RAM. And now your GPU needs to page it out. And so you're gonna see what we call like performance cliffs, as in like the performance is stable and then it goes down. So historically, there's almost like a metaphysical argument. We call, like in computer architecture, people call this the wheel of reincarnation, where people, they realize that like some acceleration is important, so you make it a separate chip. And then they bring it back to the CPU to avoid the transfer. And then it becomes so important enough that you make it like another chip. So these things tend to be cyclical. And NVIDIA is, they have this new architecture called NVIDIA Spark, which is like a local, it's like a box that you buy that you can SSH to from your laptop. It has about 128 gigs of like unified memory, and you just SSH into it, and it's like a separate box. So that uses like unified memory, for example. And unified memory is okay if you're doing like a local LLM inference, because performance cliffs aren't that big a deal. But if you're running a service that's really bad, like if you're, let's say, running a service at a company, and suddenly the app is very slow or very fast, like this causes like a bad user experience. And performance, being able to predict the average performance of your model is important enough that people would rather just have a separate accelerator. But again, this tends to be cyclical.
Thank you. Do you think Python could be a barrier for GPU speed up?
It depends. So like, I don't have this slide here, but it depends what you mean by Python, right? Like, so at a high level, you can think of like Python, like the way, for example, Torch compile works, is that it will read your Python code. It will extract out your PyTorch bits from your Python code, and then it will write to a file, Triton code, which gets compiled down to various layers of LLVM down to PTX, right? So this is called overhead, like basically, and then the question is this overhead substantial relative to your overall workload? And for the most part, it is not. Like the real overheads in machine learning are twofold. Memory bandwidth bottlenecks, because of, and that's why we need fusions. Compute bottlenecks, as in how fast is your algorithm? And that's why we need faster matrix multiplication algorithms. And then 3 is like communication bottlenecks and distributed. So hypothetically, everyone could just write raw CUDA all the time. And for example, that's what Karpathy did with lm.c. And it was faster. What you lose is flexibility, as in it takes 6 months to write one model and make it fast. Whereas with Torch compile, it takes 10 seconds for any model. So it just has like different trade-offs.
Do you think other high-level languages could replace Python?
Okay, I've tried a lot over the years. Like I was really into Haskell, I was into Julia, I was into Node. I don't know, I love Python, and like I hope Python sticks around. One argument for why Python might be more durable than we might expect is that like LLMs today are like very, very good at writing Python because there's like an abundance of data on it. Whereas like, for example, LLMs are very bad at writing CUDA or Rust, for example. And so like if this ends up being like how most people learn programming, it seems to me like we kind of get stuck with the most popular language, and then we try to recover performance with compilers. That said, like I'm sure there's still a place for higher level languages, but like I haven't regretted spending most of my professional career on Python.
First of all, thank you for the talk. Thank you for coming here. My question was, there are architectures called TPUs. they're optimized for tensors. So my question is, why aren't they used rather than GPUs in the field of AI? Since they can optimize like a lot of things, and sometimes they're actually better than GPUs.
They are used. So like the TLDR is that like GPUs and TPUs, at least for more recent generations of GPUs, are converging very heavily in what they look like. GPUs initially were graphics processors. So basically you program using triangles, like vertices to render things. And then CUDA was the first programming language that figured out how to use triangles to write general purpose programs. And so it was kind of like fitting it in sort of like this weird way. So remember when I showed you that, let me see if I can find the chart actually. So when you look at things like tensor cores are very TPU-like. Like essentially like the way they work is that you basically have a matrix in like, let's say FP16. You lay it out in memory in a very specific way to make sure that like it's very cache efficient. And this can be like dramatically faster than just like packing and unpacking weights. So like fundamentally, I think again, GPUs and TPUs for data center GPUs, I don't expect will be very different in the near future. They're gonna look very much alike. It's just like, I think NVIDIA has the benefit of they have a much larger community. You can buy a consumer card, like an NVIDIA GPU, you can run CUDA and then the same program will run on the data center. So it's more accessible to get into it. I don't think Google has like sort of a hobbyist TPU. And for the most part, like TPUs have done really well for Google's workloads, but not too much in open source because they're like slightly harder to program for. But like GPUs are also sort of like, they're easy to program for in general, but they're hard to get peak performance. So like, again, the future, they're gonna be very much alike. And even like architectures like GraphCore, Cerebrus, they all like borrow from like very similar ideas, like with the systolic arrays. So yeah, I mean, if you like computer architecture at all, it's really like a golden age of computer architecture today. And I think people are looking for good people.
I have one more question, if that's fine. All right, so my other question is, you know how Mac has neural chips and has GPU cores and CPU cores? So what's the difference of their neural chips and the GPUs of NVIDIA?
Yeah, I mean, like conceptually, like they're very similar. The main difference is that like one has unified memory when one doesn't. The other thing is that it's like integrated, and so like it's limited by like how much power it can receive and how much heat because you don't want to burn your laps. So like the trade-offs like Mac will take will be to like lose peak performance to not like literally melt your GPU. But like the way I think of it is that like if you're doing like batch size 1 LLM inference on a local LM that you downloaded, I think a Mac is great. But like personally, what I use for like my hobbyist coding is a 4090, and I love it. So yeah, I think for any sort of serious workload, I don't foresee people using Macs for deployments or anything like that. The hardware is simply too expensive. Mostly for the design, not for the performance.
All right, thank you.
All right. So thank you all for coming.
Thank you.
Thanks again, Mark. It was great.